Hey folks, Mr. Ray here with our next advanced functions lesson in trigonometry. We're going to be proving trigonometric or trig for short identities. You did this in grade 11 with less complicated questions, I'll say. So what is a trig identity? So we're going to do several examples. But a trig identity, it's an equality. So what equality means, it's like an equation. It's got an equal sign in between the left side and the right side. It's not an equation because we're not trying to solve it. We're trying to prove the equality or the identity. Okay, and one of the important things that's different or unique about proving an identity is you want to prove it for all values of the variable. Okay, so for example, you can't just see an identity and say, look, I'm going to plug in an angle, and if it works, then the identity is proven. Well, that's not true. You've just proved it works for one angle, and it may not work for any other angles, or there may be one angle where it doesn't work. Okay, I'll give you an example of that. So if I improperly asked you to prove that sine x equals cos x, right? And that's definitely not an identity. Somebody could say, well, wait a minute, if I plug in if I plug in x equals pi by 2, and cos pi by 2, those values for sine and cos for that angle happen to be the same. It'd be 1 over root 2 for both sides. But this does not prove that this is always true. You could plug in just about any other angle, say sine of, sorry, that's not pi by 2, pi by 4, sorry. Sine of pi by 4, cos of pi by 4, they both have the value of 1 over root 2. But if I plugged in pi by 2, sine of pi by 2 is 1, cos of pi by 2 is 0. It doesn't work for that. So this is not an identity, obviously, but I just want to show you a case where to show that you can't just plug in a random value and check to see if it works. That's not what identities are all about. So how do we go about proving a trig identity? Well, we have a bunch of basic identities, basic rules that we know are true, and what we do is we look at the left side of the identity, we look at the right side separately, and then we can manipulate them using existing identities, basic identities that we know are true, and hopefully turn the left side into the right side or the right side into the left side. Okay, so we'll see how that works. So what are these basic identities? Well, if you go back to grade 11, we only had these guys. We had the Pythagorean identity, quotient for tan, and then the reciprocal identities for the secondary functions. Now, for this one here, for the Pythagorean, there's actually two other versions of this that are quite useful. If I was to divide all three terms by sine squared x, I would get 1, and cos squared over sine squared would be plus that would be cotan squared x. And then if I divided 1 by sine squared x, I get cosecant squared x. So there's another version of this if we just divide everything by sine squared. If I went back and divided everything by cos squared, I'd have sine squared over cos squared is tan squared x, of course, I just leave that out. Cos squared divided by cos squared is 1, and 1 over cos squared is secant squared. So here are the two other versions of the Pythagorean identity. These do come up quite often, so it's important maybe to write them out when you start doing your trig identities, or just remember that they involve, tan squared, secant squared. They involve the other ratios other than sine squared and cos squared. So if you see something showing up with one of these, you might want to think about using one of those. This was up to here. This was grade 11. And based on the last lesson we did, we just basically doubled or maybe even tripled our list of basic identities. We have the compound identities, addition and subtraction of two angles, the double angle, which is really just a special case of the addition compound angle formulas. And then I talked about these last lesson as well, where the cofunction identities, you can turn a sine x into a cos, or cos into sine. This is about the only way you can do this. Okay, so you're going to have this list of identities kind of on your side table. Hopefully you remember some of them, so you know to go back and look here. So before we get going, I'm going to go through some strategies. I think this is something that books don't usually talk about, but some of these things are extremely useful. So I tried to put these kind of in order of importance, but they're, you could say any one of these is the most important if you really wanted to. So the first one, and this is a pretty common thing, if you see on any other trig ratios besides sine and cos, a common strategy would be to change them into sine and cos. Like if you see tan x, change that into sine x over cos x, etc. So, or if you see 1 over cosecant, change that into sine. Okay. Now this, you don't always have to do it, and we'll see examples where sometimes we do, sometimes we don't. Now, where the most basic question is always, how do you start? Well, you're going to write these left side and right side separately, and you're not going to do anything between them. It's like you have a brick wall down the middle. So you look at both left side and right side, and you usually start with the most complicated side. Okay, so that might be the one with the most terms, might be the one that's got a rational expression. The other side might not. So you try to start with the most complicated and try to turn it into the simpler side. It's usually more difficult to start with something simple, the side that's simpler, and try to change that into the other side. Okay. A lot of the things that may not be obvious is just carry out the algebra steps. If there's something in there where you can distribute, like multiply across brackets, maybe that's a good idea. Maybe you should simplify, combine terms together if you can, divide things out, maybe factor. Okay, well, factoring is the next one. Speak of the devil. Use factoring, including difference of squares. That's a really key strategy. Think about difference of squares quite a bit in order to cancel factors in the numerator and denominator. If you see one side that's got two terms and the other side's got one, work on the side that's got two terms. Try to change that into a single term by finding a common denominator and combining the two terms. This one here, this is a very underrated strategy. I'll show you what I mean by this. Multiply rational expressions by the conjugate. So we've talked about this year already when we were working with radical expressions, and you had a radical on the bottom, like 1 over root 2, and we would try to change the bottom so it didn't have a radical. But when we had a binomial in the bottom, the strategy we used was multiply the denominator by the conjugate. So even though we're not trying to get rid of a radical this time, an example of that might be, so say I had, okay, just let me draw an arrow to the one I'm doing. So this one here. So if you had one side that was 1 over 1 minus cos x, okay, and you didn't know what to do with that, right? Because, where do you go from there? So the strategy would be multiply by the conjugate of the denominator. So what's the conjugate? The conjugate, if you remember, it's same terms but opposite signs. So it would be 1 plus cos x. And of course you have to do that on the top. so you're not really changing the value. So you can see here, this is where the difference of squares comes in, sort of. These would be the factors of difference of squares. So this is like a minus b, a plus b. So on the bottom, the result of this would be a squared minus b squared. So that's going to be 1 minus cos squared x on the bottom. And then on the top, it's just 1 times that, so 1 plus cos x. And you might look at that and go, how does that make it better? It looks worse. But this is actually one of the basic identities, the trig identities. You know that 1 minus cos squared x is actually sine squared x. So on the bottom now you've got sine squared x and 1 plus cos x on the top. So that's the strategy I was talking about with the conjugate. You actually did turn it into something simpler. So if you started with this, now you've just got a sine squared x on the bottom instead of a 1 minus cos x. It seems like it might not be that great, but you'll see you can start canceling signs, whereas here there's not much to go with. Okay, so that's a very important strategy. If you get stuck working with one side, switch to the other side and try working from that end. Sometimes you can prove an identity from both sides. So you could come up with an intermediate expression on both sides. As long as you can get the left side equal to the right side, I'm okay with that. Just a word of caution, there's quite a few teachers and professors that don't like that strategy. They feel that you should be able to just work from one side and not work from both. I'm totally fine with working from both and coming up with an intermediate expression that's the same on both sides. Okay, and the last thing here, don't stress out. Okay, try to treat these identities as puzzles, math puzzles, and challenge yourself. And I know that might sound a little bit nerdy, but the thing is, even when I'm doing the same trig identities year after year, you don't remember exactly what you're going to do when you look at the question. I always start every question with a blank slate. What should I do? I don't just look at it and go, oh, I know I'm going to do these 2 steps and I'm going to end up with the final answer that I want. Sometimes it's just try something and see if it works. Okay, so let's see how we can get started with our first example here. So we're going to prove that cosecant of 2x is equal to the cosecant of x over 2 cos x. So first thing I'm going to do is write out the left side. Left side equals cosecant 2x, and way over here, right side equals cosecant x over 2 cos x. Okay, so again, remember the first thing is try to pick the side that's most complicated. Now you may look at this and go, well, they both look pretty complicated. So my next thing would be, is there any basic identities I can use right off the bat? And I see this 2x here and say, well, that's a double angle. So I don't have a formula for cosecant of a double angle, but I definitely have one for sine. So I'm going to change the cosecant into a sine. So cosecant of an angle is equal to 1 over sine of that angle. So it's 1 over sine 2x. Okay, and I do have a formula for that. We go back to our our list of identities. I've got my sine of 2x here, and that's equal to 2 sine x cos x. So that's my next step. Change that into 1 over 2 sine x cos x. Now, at this point, after you've done something, after you've achieved some kind of change, at this point I'm going to look over here and see, am I getting warm? Am I getting close? And my first thing I would recognize is, oh, there's a 2 on both sides of the bottom. I want to keep that. There's a cos on the bottom. I want to keep that, but I've got 1 over sine here compared to cosecant, and then the light bulb might go off and say, well, 1 over sine is cosecant. So what I'm going to do to make this obvious, and this is something we do fairly often, I'm actually going to I'm going to kind of factor this part outside. I could change it at that point to cosecant, but I want to show you this strategy as well. So I'm going to basically break this into 2 factors. So the first factor is 1 over sine x, and I'm multiplying that with what's left, which is 1 over 2 cos x. Okay, and you can see I want to keep that. I've got the 2 cos x perfect. Now at this point I'm going to change, kind of running out of room here. So that's going to be cosecant x times 1 over 2 cos x, and at that point I can put them together. I'm just going to squeeze this over here. Normally it would go, in a straight line, but we're running out of room. So at this point now I can change it back to cosecant x over 2 cos x, and now at this point I can definitely confirm that this left side value is equal to what we have on the right side. So we always end the identity with this statement. Very important. And the form, I'm not going to waver on this. You have to build your proof left side equals and work with that, right side way over here, and eventually once you get the 2 sides equal, left side equal right side statement, and you're done. Okay, let's go on with another identity. This time we've got secant x minus 1 over x secant x is equal to 1 minus cos x over x. So again, I'm going to break the 2 sides apart. Left side equals secant x minus 1 over x secant x. Right side equals 1 minus cos x over x. And even looking at them right now, they're both pretty complicated. They're both rational because there's a division bar here, but there's still only one term in each. There's two terms on the denominator, one term on the denominator. So I'm going to choose to start working with this, and I'm kind of comparing that right now. I'm saying I've got an x on both denominators. If I want to try to turn this into this, it means I'm going to have to get rid of secant x. Okay, so what I'm going to do, this is a trick we didn't really talk about. If I want to get rid of the secant x, if I want to get rid of secant x, if I multiply that by cos x, they basically undo each other because they're reciprocal functions anyways. So I'm going to, out front here, I'm going to multiply the whole thing by cos x over cos x. And then the rest of it is still here, secant x minus 1 over x secant x. Okay, and I can see I can actually cancel these here, the cos x with the secant x. And now I'm just left with the bottom having an x, and that's great news. So now what I'm going to do is actually distribute the top. So this is basically cos x times this two-term expression. So when we multiply that out, again, cos x times secant x, those are reciprocal. So from that, I'm going to get a 1. I'll just put this over here, cos x times secant x is equal to 1. So that's not an identity that we have on our page, but that's basically, if you multiply one of the trig identities by its reciprocal identity, its reciprocal, you will get 1. So we get a 1 from there. Sorry, we get a 1 from this, and then we get minus cos x over x, and ta-da, we, without even realizing it, we created the right side. So that's great, and that will happen. Sometimes you're just trying to clean up the bottom, like we were with just leaving the x, and everything else just falls in place on the top. So that's great news. That means we're done. We've got the left side equal to the right side. Okay. So I've got 2 more to do here. Okay, now this one looks a little more complicated. We've got prove that sine theta plus cos theta squared is equal to 1 plus 2 sine 2 theta. Okay, so I'm going to write the left side out here. Sine theta plus cos theta squared. And then the right side over here, 1 plus sine 2 theta. And I would say that this is the more complicated side because I've got something squared, whereas here I just have 2 terms, no denominators on either. So one of the strategies was to do the algebra, and what we could do here is just expand this out. So remember, this thing squared is not just sine squared theta plus cos squared theta. It involves basically doing your FOIL. So what you do get when you do this, I will get a sine squared theta, and I will get a cos squared theta. But I'm also going to get a sine theta cos theta, and then another sine theta cos theta. Just remember, this is sine theta plus cos theta times sine theta plus cos theta. So I do get that middle term from the outside-inside multiplications, and that's going to be 2 sine theta cos theta. Okay, now here's where you need to start recognizing your identities, because there's actually 2 of them right here. First one should be fairly straightforward, and that's sine squared theta plus cos squared theta. Well, that's just your Pythagorean identity, so that's 1. And that's good news because look at that, we got a 1 here, so you're thinking, well, this should be equal to that if it's true. And that is actually, that's your sine 2 theta identity, your double angle identity for sine. So I can go back and I can change this on the left side, that this is going to be sine plus sine 2 theta. And again, it just fell into place just by expanding and carrying out the algebra. We were able to get, it only took 2 steps to get to the left side being equal to the right side. Obviously, there's a bit of knowledge that has to be applied, and that's recognizing the Pythagorean identity and the sine double angle identity. Okay. It also helps the fact that, you know, maybe I saw this ahead of time and I wrote these 2 terms first and second and this term third, which allowed me to kind of group these together into the 1. Okay, so that wasn't too bad. It looked like it was going to be a lot harder, and that is the case with a lot of trig identities. They look pretty, you know, pretty scary at first, and sometimes they are, but sometimes they just fall into place like the last 2. All right, so here's our toughest one for sure. So we've got prove that sine theta minus cos theta over sine theta plus cos theta is equal to negative cos 2 theta over 1 plus 2, 1 plus sine of 2 theta. So let's break these apart. We've got our left side, sine theta minus cos theta over sine theta plus cos theta. And over here we've got our right side, negative cos 2 theta over 1 plus sine 2 theta. Now, you might be tempted, looking at these two, they're both, in terms of how many terms and the denominator, they both look pretty similar. So you might say, well, one's not obviously more complicated than the other. But you might be tempted to say, okay, I'm going to take these two formulas and just plug in what I know they are. That might not be the best idea because you're going to get something even more complicated here. So usually when we apply those, especially the double angle or compound angle formulas, a lot of times we don't do that until the end. And you may come back to this and get stuck on this side and then apply it, and you might get them to be the same. So I'm going to use a strategy here, and this is a fairly common strategy that's used. This is really the conjugate strategy I was telling you about. So on the bottom we've got two trig terms that we're adding together. So what I'm going to do, I'm going to put brackets around each of the numerator and denominator. Okay, so what I'm going to do is use that conjugate strategy, which basically means I'm going to multiply top and bottom by the conjugate of the denominator. So remember that's just the that's just the same terms with an opposite sign between them. So I'm going to get sine theta minus cos theta as the conjugate, and then I multiply the top by the same thing. Okay, now it looks like your first step looks like you're just going to make it something really horrible, but you know when you use the conjugate strategy, you actually cleaned it up really nicely. So what do we get on the top? Well, this is just this thing squared, sine theta minus cos theta squared, which doesn't help you, but we're going to expand this using our FOIL. So I'm going to get what am I going to get here? Let me think about this for 1 sec. Okay, slight change of strategy here. Instead of multiplying by the conjugate of the denominator, in this case, and you might try it and see that it just makes it worse, and then say, well, I could multiply by the conjugate of the numerator, so that would really mean I'm multiplying by sine theta plus cos theta on both sides. So let's see what happens there. So when we do this, this is like your difference of squares, a minus b, a plus b. So we're going to get sine squared theta, because it's a squared minus b squared, sine squared theta minus cos squared theta on the top. And then on the bottom, this is where this is basically squared. So I'm going to get, we did this before on the previous question, so very similar, sine squared theta from the sine times sine. We're also going to get cos squared theta. And then we're going to get our sine theta cos theta twice. So 2 sine theta cos theta. Okay, now we could tell we're kind of getting close here because this is exactly the same denominator we had in the question above. So we've got our sine theta plus cos theta. We know that's the trig identity. We also have a double angle formula here, or sorry, a compound angle formula here. We can change that. And up here, we've got sine squared theta minus cos squared theta. Now, if we go back to our, find my identities here. Okay, it looks a lot like this cosine double angle formula. The actual formula here is cos squared minus sine squared, and we have sine squared minus cos squared. Okay, so that's disappointing, but it's definitely not insurmountable. So what I'm going to do, I'm going to factor out the negative sign on the top. And when I factor that out from both of these, I end up turning this around. So this becomes cos squared theta minus sine squared theta, which is the formula that I would like to have because that's the double angle formula, okay? And you can test it, make sure this works, right? If I apply the negative sign to both, that's negative cos squared theta, and this is positive sine squared theta, so that's okay. Now we can clean this up on the bottom. We know that's a 1, so I've got 1, and then I've got 2 sine theta cos theta, which, if you remember from just a few minutes ago, that's equal to sine 2 theta, so plus sine 2 theta. And if you look back over here, things are looking really good. I've got the correct denominator. And now, the last line I do here is cleaning this up, because remember, we wanted this cos squared theta minus sine squared theta in that order, because that is cos of 2 theta. So I just replace the thing in brackets with cos 2 theta, and then on the bottom, just leave it as it was. And lo and behold, we got that one to work. Okay. Now, it's not going to be as easy as maybe I showed you on some of these examples. A lot of time, you're going to be doing work and you're not going to do anything wrong mathematically, but you might just be headed in the wrong direction. And after a while you go, this was not the right strategy. So you have to kind of bite the bullet and go back and try again. One of the most difficult types of questions, if we go back to our formulas here, is something that involves a sine, the double angle formula for cos. Because remember, we've actually got 3 different formulas for it. So a lot of times when you see a cos 2 theta or cos 2x in the formula and you want to change it, the question is, well, which one should we change it to? So sometimes you can look at the other side and say, oh, this one would be great because it's going to get me closer to my goal. Other times you might plug something in and makes it worse, and then you go back and use one of the other 2 that you didn't try. So that's a little frustrating when you get one of the cos double angle conversions because there's 3 options. Okay, so like I said, don't get discouraged when you're doing these. If you get going the wrong direction, then just go back to where you could maybe try a different strategy. So that's my recommendation. We've got some homework questions here. I've got quite a few of them here, so try as many as you need to make yourself comfortable in using this. So we'll be taking a lot of these up in class. I know the back of the book does not have the overall solution, but I'll be posting the solutions, the entire solutions, the way I did it on the class website. So again, like I said, it's not good enough just for you to watch me do 4 of these. You're not going to become an expert. You've got to try these yourself. You've got to practice. You've got to go through the pain of what it's like, so that when you see these on a test or an assignment, you'll understand that you know, I gotta just move forward. Maybe take a breather, come back, use a different strategy. Okay, so that's it for today. Hope you guys have a great day, and we'll see you in the next lesson.